We're going to start our discussion of waves here by talking about something called simple harmonic motion, which is a particular kind of oscillation. So when we talk about an oscillation, really what we're talking about is just something moving back and forth, right? So here, over here, we have a spring with a mass attached to it. And if we compress the spring, just like we did in our CART energy lab, we would see that that mass move back and forth, right? So it's going to start here. The spring is going to push it this way. It'll pass x equals 0, which is our equilibrium point. It'll get stretched out. The spring will get stretched out when the mass is over here, and that will pull it back towards the equilibrium point. And as long as it doesn't lose any energy, it'll keep going forever, okay? If there's absolutely no friction, then this motion is going to continue forever. And what's happening is we're converting energy from spring energy here with the compressed spring to kinetic energy in the middle, and then to spring energy again over here. As the object moves towards one endpoint, the force is always pushing back against that motion. So when it's here, the force tries to restore us to x equals 0, which we call our equilibrium point. But once we're past there, the spring starts pulling back on the mass to the left. So over here, over here, our force is pushing to the left. The mass starts moving again to the left. It passes the equilibrium point, and again, our force starts pushing back to the equilibrium point. So that's a basic oscillation, is that idea that we have some kind of restoring force that tries to move an object back to a midpoint or an equilibrium point, but always overshoots. And in overshooting causes the oscillation to continue. We can talk about a particular kind of oscillation called simple harmonic oscillation. And this occurs when our force follows Hooke's law. What does that mean? It just means that we have a linear relationship between position and force. As our mass moves away, either extends the spring or compresses the spring, and it moves away from the equilibrium point, the force increases with position here, right? So as x gets bigger, so when x is big X over here at its maximum point, our force is at its maximum point. And similarly, when we're at this end, x gets bigger and produces the maximum force back to the middle. When x is in the middle, there's no force at all, right? Because x here equals 0. There's no displacement. And that means there's no force. A couple of terms that we talk about when we talk about oscillation. One is period t, and I'm not sure why it's t. It sort of goes, it's a big T, so it goes with the little t time. It is a length of time that it takes to do one oscillation. So when I start here and it oscillates to the far end and comes back here, that's one oscillation. Now don't get confused, because if you think about it just returns to its same point, that's not exactly right. Because if I'm at x equals 0 and I moved my far point and come back to x equals 0, that's just a half oscillation. Okay, it still has to go to the other side. So you have to think of it as from one max all the way to the other max and back to the first max. Frequency, on the other hand, describes the number of oscillations you have in a unit of time. So here's our equation for frequency, and it's the inverse of period. So let's say I have a period t that is 1/10 of a second. It takes it 1/10 of a second to go from here over there to back here. My frequency then is 10, and the units there are hertz, so we call that 10 hertz. That means in 1 second it goes back and forth 10 times. And finally, amplitude is the magnitude of the oscillation. How far away from the equilibrium point does it get? Okay, and we have to be careful again, because a lot of times people will think, oh, the amplitude is from here all the way to here. And actually, in some fields, that's how it's measured. But most of the time, it's measured as from the equilibrium to one of the max points. That's our amplitude. So amplitude is a distance, period t is a length of time, and frequency is the number of times per second. So let's look at this, what's happening when an oscillation occurs. You got some interesting characteristics of this oscillation um, at different points in the process. So at the moment of max displacement, the velocity is 0. And we saw that in the, in our cart lab where the cart was moving up and down the ramp. You see it a little bit like when you throw a ball into the air and at the peak it stops. Okay, so the mass is moving this way and it turns around, and somewhere right at the end that velocity has to be equal to 0. So what's our kinetic energy there? The kinetic energy is 0, right? What's our force here? The force here is at a max because our displacement is at a max. We're as far as we get from here, and so our force is as large as it can be because of Hooke's law. And finally, if the force is biggest here, then the acceleration is biggest here. And this throws people too. Because it's not moving, we wonder about, is it accelerating? Well, it is, because an instant before it was traveling to the left, and an instant later it's traveling to the right. If our force is at its max, then our acceleration has to be at its max too. So we can write all of these things. Displacement is at a max, velocity is 0, acceleration is at a max. Now, on the other hand, when it's passing the equilibrium point, the force is actually 0. Okay, so we're at x equals 0. Hooke's law tells us the force is 0. And if we have 0 force, just for that instant, we have 0 acceleration. Okay, so when it's over here, the force is rightward and it's accelerating rightward. For an instant, it's not accelerating, and then once we're over here, the spring tries to restore it back to the left, and we'll be accelerating to the left. The velocity, on the other hand, is at a maximum because it's when the mass was over here, it started accelerating to the right. It's getting faster and faster and faster. This is its max velocity, and after this, the force will start to slow it down by pushing it to the left. And so we can write here, x equals 0, velocity is at the max, and acceleration is equal to 0. So those are, if we can get these straight, we'll have a pretty good understanding of simple harmonic. Why do we care about simple harmonic motion? The short answer is because it follows a sinusoidal path. If we think of this, a mass here bouncing up and down, and we make this paper roll along and we mark where the mass is along the paper as it rolls along, you get this nice curve here. And that nice curve is a sinusoidal curve, which just means it has a sine or a cosine in it. And you can see those over here. Not only does our position plot have a sinusoidal curve, but so do our velocity plots and our acceleration plots. Now we can look at these, and these plots essentially say the same thing that we saw on the last page. Okay, so if at, say, half t, halfway through my time period, my position is at a max, we know that means that my velocity is at 0, right? Because I'm turning around, and I can see that's true. And we know that the force is greatest and my acceleration is greatest because I'm far away from equilibrium. And we can see that too. So at that point, we have large displacement, no velocity, and large acceleration. We could go through and look at these plots and see the other point too, where we're passing equilibrium and we have a large velocity and no acceleration. So you notice that these plots are shifted. They look identical. They're the same shape. They're all sinusoidal. but they're shifted. So I've taken this position plot and I basically move it over by a quarter t. So like my low peak here is my low peak by a quarter t before that. My high peak here is my high peak a quarter t before that, a quarter t being the time between here and here. And so that's why these are interesting mathematically, and also they just occur all of the time in nature. This is just a nice model that can help us mathematically model everything from how an eardrum works to how a spring on a car works to how a tree waves in the wind.